So welcome everybody to this SIAM webinar of the group of the activity group on geosciences. This is actually the 7th seminar of the series, and it's given by Lynn Schreyer from Washington State University. And you can see here the title, but before I want just to give some information about the activity group. We have a YouTube channel that is also the place where we keep all the webinar that have been recorded so far. We are active on the Engage site by SIAM. And we have also 2 websites, let's say the official website and a wiki page where we put the latest news. I recall that there is a possibility. SIAM is very keen on having students member, and there is a possibility of having free membership. In particular, if you have a student chapter, a SIAM student chapter in your school, all the members of the chapter are eligible for a free membership. Or if your university is an academic member of SIAM, then again, all the students can obtain a free membership. And then I will recall that every SIAM regular member can nominate 2 students to get a free membership. I don't remember if the nomination for this year I received the mail quite recently is still open, but check, and if it is still open, you can certainly take advantage of this opportunity. News of just a few months ago, we opened a LinkedIn page, so you can now follow us also on LinkedIn. Here we post not only the announcement for the webinars, but also many other activities and news of general interest for people working on computational geosciences. And these are the next webinars. We are planning other 2 webinars this year. One will be from William D. Collins on the 8th of November, and one from John Zimmerling on the 6th of December. The time is always the same. So now let's go back to the talk of today by Lynn Schreyer. And the title is "Sometimes using a different dependent variable makes life easier, using chemical potential to model vapor transport through partially saturated porous media." I recall that the seminar is recorded and posted on the YouTube channel. You can use the question and answer or raise your hand to ask questions. And if you want, you may use the chat to say hi. So Lynn, the floor is yours, the virtual floor.
Hey, welcome everybody. And thank you for the introduction, Luca. It's always good to remind everybody the pre-membership possibility for students. And welcome everybody. Good day. Glad you could join us. So what I'd like to talk about today is the concept of chemical potential, or for a single component, Gibbs potential, and hopefully give you an introduction to the concept and show you the usefulness of it within the concept, within the frame of porous media. Most of us have not taken physical chemistry, and so we're not formally introduced to this concept. And so today what we're going to do is go through chemical potential, how it's defined, how you measure it, because it's not directly measurable. And then that will be mostly material that you would find in a physical chemistry book. And that will be some work if you have not seen this before, but hang in there, because after that, we will go through and talk directly about how it relates to particular situations at the Pore-scale and at the macro scale. So here, let's just dive in. Okay, so the motivation of how I got into it was this experiment. And the idea of this experiment is, okay, we have this is on the order of, at 5 centimeters diameter here. And the radius changes, and you can put in a bridge of water, in this case with calcium nitrate, with a concentration of calcium nitrate. And this poor master's student would tape a ruler to each side, and water would evaporate from this side, diffuse through the air, and eventually condense onto this side, causing the surface here to move up. And the poor graduate student at School of Mines, he was a master's student, would stand here for hours and measure the height of the water, or the height on this side, for every 30 couple of minutes. It was a slow process. Okay, so if you come from the flow through porous media, and a lot of people who model these sort of things do come from that side, the typical approach is to use the diffusion equation for vapor transport with concentration as the dependent variable, and in the air, and you have boundary conditions, initial conditions. Maybe you want to use the Kelvin equation, which relates concentration of water vapor to the contact angle. So this actually has kind of a contact angle here. And that includes trying to figure out the curvature and the surface tension. Then you have condensation, evaporation, and possibly incorporating microscale temperature fluctuations. And I've seen papers where they have like between 6 and 10 fitting parameters for this sort of setup. Now we're going to simplify this. For this whole talk, I'm going to assume constant temperature, so that would knock out some equations. But conceptually, this is much easier if we think in terms of chemical potential. So that's where we'll get to towards the end of this talk. Okay, so in a nutshell, chemical potential is the fundamental quantity that determines the rate at which a component changes phase. So you can think water into water, liquid water into water vapor. It's the potential that determines diffusion, and it's equilibrium. It determines the equilibrium state of a chemical reaction. So let's go back to the very beginning here, the fundamental laws of thermodynamics. So the first law of thermodynamics is conservation of energy, which I think most of us know about. The second law of thermodynamics is that entropy cannot decrease, and this law says that in an isolated system where there's no net change of mass, momenta, or energy in the entire system, a system will evolve toward increasing randomness, and entropy is a measure of the randomness. And then there's the third law of thermodynamics, which says that entropy at absolute zero thermodynamic temperature, 0 degrees Kelvin, may be taken to be zero. In other words, absolute zero cannot be achieved. So this is the foundation of thermodynamics. Resnick and Halliday, who wrote the physics books that I learned from when I was an undergrad student, they've been around for a long time, humorously refer to these three laws as: the first law is you can't win, the second law says you can't break even, and the third law says you can't get out of the game. Okay, so to start with, just to give ourselves some intuition about these thermodynamic quantities, let's assume we have a simple system, think a gas, and U is the total energy of our system, and capital S is entropy, and V is volume, and N is the number of molecules of all our components. Okay, so what we want to do is, let's start by taking the total differential here. And these first partial derivatives appear, and we define T to be the change in energy with respect to entropy. We define pressure to be change in energy with respect to volume. And we define mu J to be the change in energy with respect to number of components. Now we call T temperature, but how do we know that temperature is change in energy with respect to entropy? And we call P pressure. How do we know that this quantity is what we measure when we put a force transducer into the fluid or gas? And then, of course, we'll get to chemical potential. So in order to understand why we believe that this is so, is by considering the following thought experiment. So we have two boxes, and on one side we have a mixture of gas which has energy 1 and volume 1, entropy 1, and a mixture of components, and likewise on side 2. Now, our first thought experiment is that the wall that is separating these two compartments is rigid, means it can't move. It's diathermal, so it will allow heat to go across, and it's impermeable, okay? And we're going to use the second law of thermodynamics. So we're going to start with the total change of entropy. And so we're changing our dependent variable from energy to entropy here. And if we're going to take the total differential of each of them and add them together. And the wall is rigid. This means that the volume can't change. So dV1 and dV2 are 0. So we're going to take out that term. The wall is impermeable. So the number of molecules on each side of each type can't change. So that's 0. And the system is isolated. So the total energy is can't change. So at equilibrium, we have that the total change of entropy is, and we're going to use the fact that we're defining T1 to be the partial of U1 with respect to S1, and likewise T2. And we replace DU2 with DU1. So we get this expression, and this holds at equilibrium. Now, equilibrium is when the entropy is maximum. So if the entropy is maximum, then we get that the coefficient of DU1 is 0. And so we get that temperature 1 is equal to temperature 2. So what we found is that if we have this wall that only allows temperature heat transfer across it, that at equilibrium, we get that temperatures are equal. And this is consistent with our physical interpretation of temperature. Okay, now let's try another experiment where now we allow the wall to move, allow heat to transfer through, and to allow the number of molecules to move through. And we could do these one at a time, but we're just going to do these all together because it's the same concept. Okay, so we're going to talk about the total change in entropy. And so this is the total derivative again. Now, in this case, the total energy is still constant. The total volume is still constant, and the total number of moles of each component is also constant. So we can rewrite our total change in entropy in this way, where we just eliminated the two components. Okay, so entropy is maximum at equilibrium. That means that all the partial derivatives of entropy with respect to energy, volume, and NJs are 0. And so if we look at what happens with a partial derivative with respect to energy, keeping volume and number of molecules fixed, we get the result that we got before, that the temperatures must be equal. And likewise, if we do the implicit function theorem, we can show that this is equal to pressure over temperature. And if at equilibrium temperature is fixed, then at equilibrium pressure is fixed. So this is a result of the wall being allowed to move. So if you think of the wall as being able to move until it hits equilibrium, then you can see that it is the pressures that are equal. And likewise, since temperatures are equal at equilibrium, this last term shows us that at equilibrium, the chemical potential of each component must be equal at equilibrium. So this is our first idea of what chemical potential is. Okay, so we don't always work in terms of extensive variables. So so we need to be able to represent chemical potential in terms of intensive variables. So we can divide through by the molar mass, for example, or the number of volume, I think is what I did here. And we get, so the chemical potential defined in terms of extensive variables is just related to a constant times the chemical potential related to the intensive variables of change in E with respect to rho J. Okay, so again, and I'll just keep emphasizing this over and over again, chemical potential is a change in energy with respect to quantity. It measures, and this is just by its definition here, it measures the amount of energy it takes to take a molecule from infinity and to put it into your system. So it's just a measure of how much energy it takes to squeeze a molecule into it. The chemical potential of a single constituent in two phases are equal at equilibrium, and it's the driving force for diffusive flow. So usually we see Fick's law here, which is concentration, and we'll show that Fick's law is actually a simplification of this term. Okay, so extensive to intensive again. So extensive variables are variables that change with the quantity of material. So we have like capital S for total entropy, and volume changes with how much we have, and the number of molecules change. Intensive quantities don't change with quantities. So variables such as pressure, temperature, and chemical potential. When we go from extensive variables to intensive variables, we always lose one independent variable. So we have here that if we have the total amount of energy as a function of entropy, volume, and number of molecules, if we divide through by volume, we see that the intensive energy is a function of just entropy and then the density of each component. So which formulation to use? If you have a closed system, most problems you would formulate in terms of extensive variables. And if you're in an open system, usually we use intensive variables. So yeah, again, this is the relationship between extensive and intensive chemical potential. Okay, now another relationship. This is called the Euler relation. It's kind of a cute trick. So if we're working in terms of extensive variables and we change the amount of entropy, volume, and the number of types, number of molecules of each component by the same number, lambda, that should be equal to, then the energy should also change by that same amount. If you take this relationship and differentiate it with respect to lambda, keeping SV and NJ fixed, and set lambda equal to 1, then what you get is that the Gibbs potential, which is a variation of the energy, is the sum J equals 1 to R of the number of molecules times the chemical potential. And the reason why, so there's a specific relationship between the Gibbs potential and the chemical potential. So we'll be talking about them almost interchangeably, because for a system where you only have one component, the Gibbs potential is the chemical potential. Okay, so the next thing we're going to talk about is how do you indirectly measure chemical potential. And the way it's built up is you talk about the chemical potential for an ideal gas, and then you start making the system more complicated. But the way that you measure it always comes back to the ideal gas law. So the ideal gas law, PV equals nRT. And for a single component, there's a relationship between the chemical potential or the Gibbs potential and temperature and pressure. So we actually know what the relationship between these variables are explicitly. So if you integrate dG, which is our chemical potential for a single, ideal gas, from a reference state to a second state, then we get the chemical potential for an ideal gas. So we get mu naught, which is the chemical potential at a reference. And this is always true, just like pressure, chemical potential is defined only relative to another state. So it's the only way you can define it. Plus RT, and if you, because of the, it works out to be P over P naught, natural log of P over P naught. Okay, so this is the chemical potential for an ideal gas law. And for a non-ideal gas, you replace the pressure by an effective pressure called the fugacity. And so this P gets replaced by an F. So now we know the chemical potential for one component gas. Okay, now let's move to a mixture of gases. So we consider all components are considered perfect, and there's minimal interaction between the species. Okay, we assume Dalton's law, where the sum of the partial pressures is your total pressure. And we have the relationship for each component satisfies an ideal gas law. And we assume an ideal mixture, so the partial pressure is related to the molar fraction of the total pressure. So substituting all that in, we get that the chemical potential, okay, now here I put a J indicating that this is one component in a mixture, is related to what that chemical potential is at the standard state, plus you have how the chemical potential changes due to pressure and how the chemical potential changes due to the molar concentration Xj. Okay. So since the molar concentration is always between 0 and 1, and the natural log of a number between 0 and 1 is negative, we have that the chemical potential of a component in a mixture is always less than the chemical potential of a pure substance. So for a gas, and we will see that it always likes to flow from high chemical potential to low chemical potential. You will never see a natural system where like all the oxygen molecules are in one side of a room, because the chemical potential will be lower if the oxygen mixes with the rest of the gas. And so that's the way the gas will move. Okay, so now we know how to measure the chemical potential of a gas. Now we want to move to a liquid. Okay, now suppose that we have a pure liquid, so it's not a mixture, it's just like pure water. That's what we're going to be thinking of primarily. And that that component in the gas phase is ideal. Okay, then at equilibrium, the chemical potential of a single component in two phases are equal at equilibrium. And this comes from the second law of thermodynamics. It's a little more involved than what we did earlier in our thought experiments, but we can show this from the second law of thermodynamics. So this means that the chemical potential of liquid, and this P means pure, so it's pure water, there's no mixture, is equal to the chemical potential of that same component, which is now water in gas phase. And that is related to the chemical potential of water vapor at the standard temperature and pressure, plus any change due to pressure. Okay, so that's now the chemical potential of pure liquid. If you go back to the ideal gas law and you know what the chemical potential is. Okay, now suppose that instead of pure water, we have a mixture of water. And again, we assume that LJ is an ideal gas law when it's in the vapor phase. Okay, so again, the chemical potential at equilibrium between two phases is equal. We know that the chemical potential of the water component of the liquid is equal to the chemical potential of the water vapor. And again, this is given by the chemical potential at standard pressure plus the change in due to the change in pressure. Okay, well, now we can we can rewrite this in terms of the water in the liquid phase, where it's all pure, all just a single water phase. So we're writing the chemical potential of the liquid water component in terms of the liquid in just all liquid. Plus, and if we go through the math, this P naught becomes PGJP. So the pressure of the gas, if there was only gas phase in the air. And this is what is called the activity here in general. So this is ideal, this is activity. And for water, AJ is the relative humidity. And this is huge because relative humidity is directly measurable. So this is why we went through this change of variables. So what this says is that the chemical potential of a component of water or a component in the liquid phase is equal to the chemical potential of that pure component plus plus a term that's related to the relative humidity, which we can measure. Okay. So instead of going back to the gas phase, we can also measure the activity through an osmotic experiment. And so here we have an experiment where we have pure water on the left side and say water and sugar on the right side. And these are separated by a semi-permeable membrane that allows water to go back and forth, but does not allow the sugar to enter the left side, okay? And what you'll find is that this side will be slightly higher than the pure water side. And if you increase the pressure by an amount pi, then okay, that's something that's actually measurable. And if we go through the relationships that we know, and again, this can be found in a physical chemistry book, then what we find is that, okay, we have this relationship. This is the chemical potential on the left side, which is not changing. And then we have the chemical potential of component J, and this is again for I didn't put the P here, there should be a pure here, for just pure water, which is the same as this chemical potential over here. So what we have is this term is equal to this term, so this term must be 0. And so we have a relationship between this pressure pi and the activity again. And for this talk, I'm assuming temperature is constant, but if it's not constant, you just have to take that into account. So that's a more direct measure of the chemical potential or the activity, which is directly related to chemical potential. Okay, so let's compare the chemical potential of a liquid with the chemical potential of an ideal gas. Okay, they're both related to their pure components at standard pressure. That's kind of the reference frame. And we have that there's kind of a concentration, like this is the molar fraction for the gas. This turns out to be relative humidity for the liquid and a pressure component. And so if we're thinking of water vapor in an atmosphere, then the difference in the pressures, PG over P naught, is approximately 1. And we see that the chemical potential is primarily determined by concentration, XJ, or relative humidity. For a pure liquid, okay, that means AJ is about 1. The chemical potential is primarily determined by liquid pressure. So that's why in general we have like water moves from high pressure to low pressure, and we think in the gas phase that a component moves from high relative humidity, water vapor moves from high relative humidity to low relative humidity. Okay, now Fick's law. So we can show from the second law of thermodynamics that the diffusive flux is directly related to the gradient of the chemical potential in general. This is the more general form of Fick's law. We know that the chemical potential is a function of temperature, pressure, and molar fraction. So if we take the gradient of the chemical potential, we get a coefficient times the gradient of concentration plus a coefficient times gradient of temperature. And so what we find is that if we're neglecting temperature, gradient of temperature, and pressure, then what we have is the traditional Fick's law. So that's where Fick's law comes from. Okay, so in summary, we have the following properties. The chemical potential is the change in energy with respect to quantity. The chemical potential of a single constituent in two phases are equal at equilibrium. This is how they derive what the chemical potential is for a liquid phase. And it's the driving force for diffusive flow. Okay, now we get to have some fun. Okay, so suppose we have 3 tanks here, and we have pure water in the first one, water with, the salt didn't appear. I don't know why this word didn't appear here. Water with some salt and water with more salt, all right? And so the question is, which way does the salt move and which way does the water move? So I'll let you think about it for a second. And the idea is that water, let's start with water. Water will move from high chemical potential to low chemical potential. And when water is in a mixture, it will always, the chemical potential is always lower. So the water is going to move left to right. Now, the salt will move in a way, I don't know why that salt word just doesn't want to show up here. The salt will want to move from high concentration to low concentration, everything else being equal. So the salt will move right to left. Okay, now, what is the relative humidity just above the surface of the water in salt water? Okay, so remember, relative humidity, if temperature is constant, is directly proportional to the chemical potential. And the relative humidity above pure water is 100%. That's like the definition. So what happens? Well, once water is mixed with something, then the chemical potential is lower. So the relative humidity above salt water will be less than pure water. I have no idea if these numbers are correct. I just threw in some numbers, all right? So the idea is the more mixed water is with something else, the lower the chemical potential, the lower the relative humidity is above it. Okay, so now let's consider 2 straws in bulk water, and the water, due to the hydrophilic nature of the straw, water will go higher for a thinner straw than a thicker straw. So where is the liquid water chemical potential highest? And for water vapor, we're just thinking in terms of relative humidity. So I'll let you think what the relative humidity is up just above the water here, in the straw just above this interface, and in this bigger straw just above this interface. And I'll let you think for a second. Okay, now if it's a flat surface here, the relative humidity here is 100%. So that's our frame of reference here, 100%. Now, because this is hydrophilic, hydrophilic, this water prefers to be near the straw, near the surface of the straw. This is going to lower the chemical potential, okay? And so, or you could think in terms of the gradient. Suppose the relative humidity in the air is 20% and this is 100%. The relative humidity will be linear. And so up above here, this is going to be less than 100%. So these are hypothetical numbers. This is a measure of matrix potential, for example. Okay, well, we can go backwards. What happens if the straws are hydrophobic? Black straws, for instance. So now the water's below the surface. So now what is the relative humidity near the water gas interfaces here? And they're actually above 100%. What happens? Okay, so now let's do some modeling. We can rewrite Fick's law in terms of relative humidity. We have to be careful what the diffusion coefficient is because the diffusion coefficients are typically measured in terms of having concentration as your dependent variable. So here we're using relative humidity, so we have this additional terms in here because of that. And so define all the coefficients here. D is the diffusion coefficient, temperature, phi is our relative humidity. We're going to assume that air is composed of two ideal gases, water vapor and all the other components, which we'll just call GA. We're going to assume temperature fluctuations are negligible. So not that they're zero, but that they're negligible. That gas phase pressure fluctuations are negligible. And that water vapor is sufficiently dilute so that the density of water vapor is not influenced by the amount of the water vapor density is constant, and that the net velocity of the total gas phase is negligible. Then if we make all those assumptions, this is the conservation, it's the diffusion equation in terms of relative humidity. So it looks like we just replaced concentration with relative humidity, but it's actually a little more complicated than that, but that's what we end up getting. Okay, so we started in this problem, the experiment that I showed you at the beginning of the talk, by trying to understand enhanced vapor transport. So this is the idea that was observed many years ago. And the idea is that if you measure vapor transport through a dry porous media, and then measure vapor transport when there's moisture in the porous media, the vapor transport is much higher when there is water, liquid water in the porous media. So that is called enhanced vapor transport. And again, we're back to this experiment. So this experiment was done by Thomas Silverman, who was a master's student of John Wilson. Some of you may have heard of him at New Mexico Institute of Mining and Technology. And okay, so let's think, again, we could model it with using pressure and concentration as dependent variables, but let's see what we can do. So the first thing we're going to do is not consider the relative humidity everywhere, but we're going to average it across the cross-sectional area. And when we do that, we get what's called the Fick-Jacobs equation. And we have to take into account the change in the area into our diffusion equation. Okay. All right. So we first validated the Fick-Jacobs equation by comparing it with a three-dimensional full-scale model. And if we this position is the position from the surface of the water here. And so this is the internal diameter of the experiment. And you can see that it goes from 3.5 milliliters here. And then of course it's the widest here. And then it's narrowest here. And then we're averaging across it. And okay, so we validated that part of it. That was pretty easy. Okay, so now let's think about what's happening here with no bridge. Okay, we have pure water here. So on the surface here, we have relative humidity 100%. On the right-hand side, we have water with lithium chloride in it. And so why lithium chloride? Well, first, we want water to go from left to right. So we're going to put a mixture here because that lowers the chemical potential. And it turns out that lithium chloride has a property that when the water is saturated with lithium chloride, the relative humidity above it is 10%. So definitely we'll get water going from the left to the right. And then as water condenses here, if you just keep a solid amount of lithium chloride on this side, you can keep this saturated even as you add water due to the evaporation, the transport, and the condensation. So we have definitely this boundary condition, even as the water level rises, as the liquid level rises, is at 10%. And so we can compare the data with this line that we got, and no problem, it matches pretty well up to experimental error. Oh, it's not 10%, it's 11%. Okay, now we want to put a liquid bridge in here. Now, why did they have to add in calcium nitrate into this mixture? And the problem, if we use just pure water to make this bridge, is that the relative humidity on our boundaries here would be such that in this experiment that the liquid bridge would just evaporate and eventually be gone. So they added calcium nitrate, which has which allows the bridge to reach a particular length after the experiment's run, so that the length after a while does not change anymore. So, okay, left side, the relative humidity is 100%. The right side, the relative humidity is 11%. We need an initial condition here. So we need to know the relative humidity on either side of the bridge. So how do we get that? Well, you collect data. And I was working with a student who he wanted to get his hands in the lab, and he went in and he measured it. So what happens, he measures he takes different concentrations of water with calcium nitrate, measure the relative humidity, and of course, as the concentration goes up, the relative humidity goes down. So we know that as the concentration changes, we know what the relative humidity is on either side, because as the bridge length changes, the concentration is going to change. Okay, so for the experimental setup that was measured at the initial condition, we learned that based on the concentration that they put in here, they injected, the relative humidity on either side of the bridge is 71%. So we have 100%, 71%, 71%, and 11%. So the water level on the left is going to go down as it evaporates, and the liquid level on the right is going to go up as water condenses. What about inside here? Is the chemical potential going to change when we're in the bridge? And so it could change if the concentration had a gradient in here. And so on a first pass, we neglected that change, which means that the chemical potential on either side of this bridge is going to be the same all throughout the bridge. Okay, so our initial condition is just what I said. we're going to have, based on, as an assumption, we're going to assume that the average relative humidity is going to be linear between the left boundary and the left boundary of the bridge, and on the right side of the bridge to the right boundary. Okay, so we have the sequence. Change of the bridge volume is calculating, use the difference in mass fluxes between each side, because the difference in the relative humidities are different on each side. So there's going to be a different mass flux. Then the new bridge concentration and the resulting relative humidity is calculated. And then the position of the liquid gas interface are updated based on the mass fluxes. So here we go. So blue is our initial condition. So we're approximating in the liquid phase that the chemical potential or relative humidity is constant here. And we can see that the gradient in relative humidity is higher on the right side than the left side. So we're going to have more mass transfer. We're going to have a higher rate of mass transfer on the right side than the left side, which means the bridge position is going to move to the left faster here than this position will move to the right. And that's what we observe. And if we compare the level change with experiments, with the experimental measurement, again, we got within experimental error. And this was work that was done with Addassi, who was a student in Denmark and visiting me for a while, and Johannesson and Lynn, who are Johannesson was working with Muad. Johannesson is now in Sweden, and Professor Lynn was a chemistry professor who helped us with the experiments. Okay. All right, so now that's at the pore scale. So now we want to go to the macro scale. And the first question is, how do we define a macro scale chemical potential? And the first thing is that it should represent change of energy with respect to quantity. The chemical potential of the species in two phases must be the same at equilibrium. And the rate that phase changes should be proportional to the difference in the chemical potentials. And the Gibbs potential should be the weighted sum of the components of chemical potential. So it should mirror what we know happens at the pore scale. Yeah, this is kind of a little out of place. But if you have seen the ink blotter effect and why we have hysteresis in evaporation problems in porous material, now we kind of have a feel, we can explain it, right? So the chemical potential when the surfaces are closer together is lower. So the water is, the chemical potential here is lower than when the surfaces are farther apart. So we can think, for example, that when we're drying, here the relative humidity might be like 40% in equilibrium, whereas in this larger tube, it might be like at 70%. And so water wants to go from high to low chemical potential. So water wants to go up in this case to try and keep it. So it's hard to get this to drain. And the same thing with wetting. If this is 40% and this is 80% here, and the chemical potential says that water wants to go from high relative humidity to low relative humidity, that means it's hard to get the water to move into this bulk phase when we're wetting. And that's one of the primary contributions to hysteresis in macro scale. Okay, so one of the places that has used macro scale chemical potential as a dependent variable is in the modeling of wood. And in particular, I thought it was really great. They did this experiment where they were able to model the hysteresis in wood, of wetting of wood, and actually the swelling of wood, and by measuring the relative humidity versus the moisture content. And then there's a third parameter, which is pressure. So as wood is the change, if you load wood with a pressure, you're changing the geometry of the wood. So we're adding another dependent variable. So we have chemical potential and pressure. And once they had that data, though, they just input these curves into their model, and they were able to reproduce experimental results very nicely. Okay, what about swelling porous media? So swelling porous media means that you start with a porous media, it swells up as it comes into contact with water. So for instance, the drug Aleve, it's a long-lasting version of ibuprofen. The way that drug is delivered into our system is you insert the drug into a polymer, a swelling polymer, and you lace it. And then when you swallow it, it comes into contact with body fluid and it starts swelling, and then the drug diffuses out. So that's one example of a swelling porous media. Clay is another example of a swelling porous media, expansive soils, and of course, cooking is another example. It's a lot of foods. The reason why is porous media swells is due to microscopic forces and also macroscopic forces involving charges. The one common thing about most swelling porous media is the surface of the solid component is often charged. Okay. What is one of the primary ways of measuring how much swelling porous media swells is through a reverse osmotic pressure experiment. This was originally done by Philip Lau in '94. And this should look very familiar. We have clay solid and water, Mount Maronite in this case, and a semi-permeable membrane, and pure water on the right side where only water can go across the membrane. And the idea is we apply a pressure and measure how much water is in the system by whatever parameter Philip Lau used, the distance between platelets. This should look very similar to the experiment of water and sugar water, right? And we're measuring the pressure. And so Philip Lau was able to come up with this exponential relationship. And what we were able to do is using the concept. Okay, so first off, before I get into that, the boundary condition between the left and the right side is not a balance of pressures. Okay, I see this in papers occasionally when I review. It is, however, that the chemical potential of the water on either side is equal. So that's the boundary condition. But because of this mixture on the left-hand side, the pressures are no longer equal. So what is the relationship between the pressures? And what we can show mathematically is that the pressure in the liquid phase is equal to the pressure in the clay side, this thermodynamic pressure, plus this other pressure, pi L. And thermodynamically, pi L is the change in energy with respect to moisture content. It's like if you just replace this with respect to concentration, a similar thing. If we assume that the clay platelets are not interacting, then this pressure is determined by keeping the Gibbs potential fixed. And we define the macroscale chemical potential, which is the amount of energy it takes to take a particle from infinity and insert it into our porous media system. And well, I guess I didn't finish it. What I showed was what you can show is that this pi L is exactly, it can be, we can get directly to the relationship that Philip Lau has derived experimentally, obtained experimentally. So using the fact that the Gibbs potential is continuous between the interface. Okay, Darcy's law is actually if we write it in terms of chemical potential, it becomes much easier. It's actually just the gradient of the chemical potential of water. That's the driving force for the movement of fluid through a porous media. And because at equilibrium, the chemical potential between say bulk phase fluid and the fluid inside a porous media are continuous, you only get flow if the chemical potential on the left is different from the chemical potential on the right. So in this case, even if you have swelling porous media in here, well, it's swelling because it's gotten higher than atmospheric pressure, you won't have flow in this first case because the pressures are equal. Here, the pressures are still equal, and we apply a load to this a differentiated load to our swelling porous media. And if we're at equilibrium, we are still not going to see flow here. But even if you have no load, if you have a difference in pressures here, that changes the chemical potential in the bulk phases, which in turn changes the chemical potential on the boundaries of the swelling porous media, and that will induce flow. Okay, one last thing. How are we doing? Yeah, we're running out of time here. I Googled last night what matrix potential, that's what's commonly used, especially people who are working with plant roots. And if you Google it in Wikipedia, you get water potential, which I think is actually a better name for it. And they list all these components. They list, okay, there's the reference, because chemical potential is actually a reference, right? Then there's the component due to osmotic potential, pressure, gravimetric, humidity, and potential due to the cohesion and surface tension. Well, this is due to concentration of water in the liquid phase. This is like the straw effect, right? But relative humidity at equilibrium is the chemical potential of water in the liquid phase. So when I looked at this, I was like, okay, there's some redundancy here, right? But then I thought, wait a minute, all of the measurements that we are taking using relative humidity assumes that we're at equilibrium. And so if you're not at equilibrium, then maybe relative humidity could be considered as independent from these other effects. All right, so that was all I have. I'll just leave this slide up. And thank you all for your attention.
Thank you, Lynn. Quite interesting. I have revised a little bit my old studies in thermodynamics. Are there any questions? You can ask questions either by typing on the question and answer, or just by raising hands, and or just by, I think, by talking.
I can quickly ask while people are thinking of their questions. I always abuse my power as a panelist. So I realized I need to go back to some thermo as well. Thank you. That was an excellent review. So has anybody modeled this directly or this much detail, especially on the interfaces part, using Pore-scale models? So Pore-scale models where I have tubes and interfaces that are fairly well described, combined with the multi-phase flow, which they're often used for, strikes me as a cool tool to kind of compare to upscaling via Darcy's law.
Yeah. No. Okay, I don't know, but that doesn't mean there hasn't been anybody. I mean, I can imagine okay, we have a template now with this one experiment with a bridge. But the interface would have the same property. The chemical potential, if you can measure the relative humidity, right, near the interface of the interface, then you have the chemical potential. And so it's a measure of the adhesiveness of the water, the hydration of the water to the surface. Now, where chemical potential is not nice, let's see if I can go back here, is in transport. So
okay.
it's not trivial because the continuity equation and the momentum balance are not naturally in terms of chemical potential. And I think that's the biggest drawback. So, you know, what I did was mostly diffusive and condensation, you know, condensing and evaporation, which is naturally the chemical potential is the way to go. But if you put flow in there too, then it becomes a little trickier. Although there's a relationship, right? You can calculate the chemical potential in terms of pressure. So,
Right. And given that pore network models actually strike me as a bit of an ad hoc, you can kind of put things together.
yeah.
And I know that there are some, I just do not know their details. So I'm not certain if they align precisely with these ideas or what are they doing.
Yeah, no, I don't. And
A
that's
little bit
why
of
I'm putting
literature
this,
searches.
yeah, but this
in
is
order.
why I'm putting this out there, because I think it's way underused, this whole concept.
Well, part of it is computational complexity of doing two things at once, like coupling, right? That's why it's a little bit underused. Right?
Yeah.
I agree.
If anybody knows answers, please raise your hand. We can unmute you or ask a question in Q&A.
No questions?
No
Like
question.
that. No? Just a curiosity that is linked to the comment of Masha. You are here claiming and was convincing that for a certain type of processes, using chemical potential may let's say, give a better insight or even simplify things with respect to other type of models. Is this message passing through also in some, let's say, software simulation tools around, or is people more willing to stick to the old way of
Yeah.
doing?
One place is, and I'm not absolutely sure, but I believe that if you get heavy into chemical reactions, then I think chemical potential is built into those codes. So, but I'm not absolutely positive about that.
You said that anyway, it's one of the assumptions is the chemical equilibrium, right? If I got it correct to use it.
Well, for measuring the chemical potential,
Okay.
Yeah, once, you know, so for instance, suppose that the primary thing you're looking at is evaporation rates, right? If you're at equilibrium, you're not going to see any evaporation, but the rate of evaporation is directly proportional to the difference in the chemical potentials. So that means you don't have to measure the surface area tension, right? You just have to know what the chemical potential is on one side of the interface and the chemical potential on the other. You have to measure that coefficient, but it's one coefficient, and yeah, it should work.
Yeah. Thank you. Thank you for your talk. If there are no other questions from the audience, I thank you again for your nice presentation that will be put on our YouTube channel playlist, more than channel, quite soon. And thank you. Have a nice day. Here is getting dark, while instead you have still a lot of lights.
Oh, we have a lot of day left. Thank you again. I learned a lot. I also learned how much I don't know. That's the scary part.
That's always
I know.
true. Always
I
true.
just see there my Cullen book, Thermodynamics, an introduction to
Time to put
thermostatics.
it down. Time
So
to put it down, Luca.
Yeah, but what I learned is that this stuff isn't a physical chemistry book. That's where you have to go.
Yeah, okay.
It took me a long time to find that. Yeah.
A lot of standard thermo does not always like have the multi-phase part or multiple.
Components, yeah.
There might be change of phase of one thing, but having multiple components, multiple phases, that's the fun part.
Okay,
All
thank
right.
you. And have a
Alrighty.
Thank
nice
you,
day.
everybody.